Amines are fundamental organic compounds with distinct reactivity patterns. One of the most important ways to distinguish between different classes of amines is their reaction with nitrous acid, which serves as a powerful diagnostic tool in chemical analysis. Nitrous acid is highly unstable and must be prepared in situ, usually by reacting sodium nitrite with a strong mineral acid like hydrochloric acid at low temperatures. This reactive species is the key to the transformations we will study. The reaction begins with the protonation of nitrous acid to form the nitrosonium ion. This highly electrophilic cation is what actually attacks the lone pair of the nitrogen atom on the amine molecule, initiating the chemical change. Primary aliphatic amines react with nitrous acid to form alkyldiazonium salts. However, these salts are extremely unstable even at low temperatures and decompose immediately to release nitrogen gas, which appears as characteristic effervescence in the test tube. The decomposition of the diazonium salt leaves behind a carbocation. This intermediate reacts further to produce a mixture of alcohols, alkenes, and alkyl halides. The evolution of nitrogen gas is the primary visual indicator for this reaction. Unlike aliphatic amines, primary aromatic amines like aniline form relatively stable diazonium salts if the temperature is maintained between 0 and 5 degrees Celsius. This stability is due to the resonance stabilization provided by the aromatic ring. The positive charge on the diazonium group is delocalized through the pi system of the benzene ring. This resonance makes aromatic diazonium salts invaluable intermediates in synthetic organic chemistry for creating dyes and other functionalized aromatics. Secondary amines, whether aliphatic or aromatic, react differently. They react with nitrous acid to form N-nitrosamines. These compounds typically appear as yellow oily liquids that are insoluble in the aqueous reaction mixture. In secondary amines, the reaction stops at the nitrosation stage because there is no second hydrogen on the nitrogen atom to allow for the dehydration steps required to form a diazonium ion. Thus, no nitrogen gas is evolved. Let's compare. Primary amines yield nitrogen gas bubbles, while secondary amines yield a distinct yellow oily layer. This difference allows chemists to quickly identify the substitution level of an unknown amine sample in a laboratory setting. Consider ethylamine, a primary aliphatic amine. Upon adding nitrous acid, you would observe immediate bubbling as nitrogen gas escapes, and ethanol is formed as the major organic product in the solution. Now look at diethylamine, a secondary amine. Instead of bubbles, the reaction produces N-nitrosodiethylamine. This substance separates from the water as a characteristic yellow oil, indicating the presence of the secondary amino group. With aniline, a primary aromatic amine, the reaction must be kept ice-cold. If successful, you obtain a clear solution of benzene diazonium chloride, which can then be used for coupling reactions to form vibrant azo dyes. Even aromatic secondary amines like N-methylaniline follow the secondary amine rule. They react to form N-methyl-N-nitrosoaniline, which also appears as a yellow oily insoluble substance, confirming its secondary nature. It is crucial to note that N-nitrosamines, the products of secondary amine reactions, are known carcinogens. These reactions should always be performed with proper safety equipment and disposed of according to hazardous waste protocols. To summarize, primary aliphatic amines give nitrogen gas, primary aromatic amines give stable diazonium salts at low temperatures, and secondary amines produce yellow oily N-nitrosamines. These distinct results are essential for amine identification. Test your knowledge: which amine would produce a yellow oily layer when treated with nitrous acid? If you chose dimethylamine, you are correct, as it is a secondary amine and forms an N-nitrosamine. Understanding these reactions allows for the precise characterization of organic nitrogen compounds. By observing physical changes like gas evolution or oil formation, we can map the structure of complex molecules. Generated by Vision Solve AI.